Today, we're going to continue looking at limits in continuity. And I'd like to start by identifying the points on this function, f of x, where the function is discontinuous, and also where the function is undefined. So pause the video and take a few minutes to identify the points at which this function is discontinuous. Welcome back. So what are some of the points that this function is discontinuous? Anybody have one? So f of x is discontinuous at 1. Where else? At 2, 3, yeah. Yeah. What else? And 6. Sounds good. So at each of these points, something is happening. Intuitively, to draw the function, we have to take our pen off of the paper to continue drawing the function. That's our intuitive idea of it. It's not very good, but it gets the point across. So in that sense, pretty good. So at each of these points, we'd have to stop and move our pen because things are not connected. So what's happening at 1? What did we call that? What's going on at 1? There's a hole. We have a hole at 1. Oh, asymptotes are red, so I'll use orange for hole. So it's a pretty obvious hole when x is equal to 1. The graph is cruising along, disappears when x is equal to 1, and immediately reappears on the other side. Awesome. How about at x equals 2? We've got a jump. Jumps are green. So we're drawing the graph. Looks like it's going to be headed up to this value of 2. But as soon as we get past 2, immediately the values of f jump up to around 3 and start decreasing. So there's a jump there. What happens at 3? Another jump. The graph looks like it's headed towards 2, but then once we get to 3, the values of the function drop down to near 1 and then continue on. So there's another jump there. What about x equals 4? We have an asymptote. So on the left side of 4, the function is heading off towards infinity. On the right side of 4, the function is dropping down from infinity. Nothing is going on at 4. Awesome. 5 was an okay point. It's just kind of a pointy corner. And what's going on at 6? Well, this could be like, we could classify this as a hole, but the function is defined. So it kind of like jumps up to a value and then immediately jumps back down. So it's like a hole or a jump. These aren't technical terms, so it would be crazy if I said that's a hole in the graph, and you said it's a jump in the graph, and I said you were wrong, or the other way around. So we can see the problem is that we think the function is headed towards 2, but the value of the function when we get to 6 is up at 3. So it like jumps up to 3. But then when we're coming from the other side, the function says, I'm headed towards 2. From both sides of 6, the function is saying, we're headed towards 2. But then when we get to 6, the function is like, oh, nah, just kidding, I'm 3. So it jumps up to that value. So here are all the places where the function is discontinuous. Is the function undefined at all of these points? No. Is the function undefined at 1? Yeah, there's no value there. But what's the value of f at 2? F of 2 is equal to 2. So there's a filled-in spot here at 2. So here, f of 2 is equal to 2. What about 3? Undefined. 4? Undefined. In kind of almost the worst way. About 6. F of 6 is equal to 3. So oops. So it's not just that the function is undefined at a point that makes it discontinuous. The function can be defined at a point, but still be discontinuous at that point. Oops. So x equals 1, 3, 4. And that's it. F of x is undefined at these 3 points. From what we have, f is defined and continuous everywhere else. So based on what we have, the information that we have, f of x is defined and continuous everywhere else. If I came along and said, oh, the function is not defined at x equals 10, that would just be me cheating by not giving you information that I secretly knew, right? So if I give you a function and there's no obvious discontinuities and you say the function is continuous everywhere, that is correct. Based on the information, that's what we should conclude. Okay. So we notice that a function doesn't have to be discontinuous, or the function doesn't have to be undefined where it is discontinuous. But is it possible for a function to be continuous if it is not defined? Is it possible for a function to be continuous and still defined at a point? Or sorry, still be and be undefined at a point. Continuous and undefined. Is that possible? Let's go back to our intuition about what it means to be continuous. Our intuition, even though secretly we know this is not a great explanation, but it seems to get the job done. Our intuition is that we can draw the functions without lifting our pen from the paper. But if a function is not defined at a point, then I'm going to have to jump. I don't get to write anything there. Even though I'm drawing these gigantic circles at these points where the function is not defined, that's just to highlight. That's like zooming in. It's like zooming in and saying there's a big hole here. It's not actually that big. It is exactly missing the value for one real number. So there's no way to draw the function without lifting your pen off the paper if the function is not defined there. Because if the function is not defined, we don't get to draw anything there. It doesn't count at 4 where we drew an asymptote because that's not part of the function. That's really just for the reader's benefit. The function doesn't care about it. The function doesn't see no asymptote. It just says off to infinity I go. And then on the other side, back from infinity. I draw it this way because it's like all whoop. It has sound effects. Every time I draw a vertical asymptote like that, that's what I hear. I don't know why. If I draw an asymptote the other way, one goes up one side and then it comes up this side here. It's like Mario World style, or more like asteroids. I still just start hearing Mario World. I don't know if anybody's played Mario World. That game's older than all of you. Anybody remember Super Mario World? Nintendo? Cartridge games? NES. Video game enthusiasts in the room. I have a working Atari 2600 for those of you who are not exactly in this condition, and it is not a heavy six. Have I gone too far yet? Everybody know what an Atari 2600 is? And I have crossed the line. You can go far back as Nintendo, but not so far back as Atari 2600. At least I think it still works. The joysticks are broken and I have to fix them. But that's one of the things. It's just like a little circuit board and I just have to resolder some points because it's old. Any questions on the continuity of this function? How's everybody, okay? Calculus still easy? I like the caution for now. If you start off too easy, then people will like bail. Then they come back a month later. It's like, oh, when did this get difficult? And then you'd be like, oh, like 2 weeks ago. Or you'd be like, if you've been here the whole time, it's like, oh, it never did. You just disappeared. You decided to make it difficult. All right. This is how we need to start, what we need to start talking about continuity in a rigorous fashion. But we have found one thing. If a function is continuous at a point, it must at least be defined at that point. That's some facts that we have in evidence. Here's a fact that we have in evidence. If f is continuous at x equals c, then f of c is defined. We have to have some value. Now let's think about some of the points on that previous example. See what our problem was. Recall the point where x is equal to 6. We had a hole in the graph. I think it was concave down. Concave down now. The hole happened when y is equal to 2 and the value of the function was 3. So recall that the value of the function was defined when x equals 6. F of 6 is equal to 3. F is discontinuous at x equals 6, and f of 6 is equal to 3. So there was another problem. When we look at what the function is doing near 6, the function near 6 is headed towards 2. So the function is discontinuous when x equals 6, but f of 6 is equal to 3, so the function is defined. That's what we're pointing out here. F is defined at x equals 6, but there's another problem. It looks like from the left, the function is headed up towards 2, and then from the right, the function is headed towards 2. From either side of 6, the function is headed towards 2. On either side of 6, the values of f of x, is headed towards 2. So if we plug in values of x that are close to 6, but not 6, we get values that are close to 2. Plugging in values of x close to 6 gives values of f of x that are close to 2. All my pens are rebelling. I put a dead one back in. Plugging in values of f of x that are close to 6 is giving us values of values of f of x that are close to 2. So the function is headed towards 2 on both sides. But when we get to 6, the value of the function is not 2. It's not what we expect. So that's specifically what's causing the jump in this case. The function was headed one place, but the value at that place jumped. It wasn't where it was supposed to be. One of us was driving south on I-5 towards Bakersfield. Another friend was driving north on I-5 towards Bakersfield. But when we got to where Bakersfield was supposed to be, it wasn't there. Someone stole it. That would mean I-5 is discontinuous. at x equals Baker field. Any questions? Okay. So that was the problem there. The value of the function did not match expectation. Let's look at another point on the function. Let's take a look at what's going on with x equals 3. At x equals 3, we had another jump. Remember the values, 2 and 1. As we're approaching x equals 3 from the left, the function is headed towards 2. As we're approaching x equals 3 from the right, the function is headed towards 1. So we're approaching different values from either side of the point. That's what causes the jump. F of x is headed to 2 on the left 3, and f of x is headed to 1 on the right of 3. That means when we get to 3, the two sides of the function, we're headed to different places. One of us was driving south towards Bakersfield, the other one was driving north towards Las Vegas. We were headed to different places. Any questions? So we need to describe this language. When we're plugging things that are close to 3 on the left, it looks like the function is headed to 2. When we're plugging in values of x that are close to 3 on the right of 3, so slightly larger than 3 on the positive side of 3, then we're getting values that are close to 1. So we need some language for this, and then we need to fix this term to make it nice and rigorous. In this case, we would say that the limit as x approaches 6 of f of x is equal to 2. So in this case, we'll say that the limit as x approaches 6 of f of x is equal to 2. Intuitively, this just means as we plug in values that are close to 6, we're getting values for the function that are close to 2. So that's the limit as x approaches 6 of f of x equals 2. All my pens are betraying me. Maybe it's the page that's betraying me. The limit as x approaches 6 of f of x is 2. You can switch the as and the of around. Say the limit of f of x as x approaches 6 is 2. That sounds weird to me. I don't know why. But both are perfectly fine. The problem here is that the limit is 2 as we approach 6, but the value of the function is 3 when we get to 6. In the case of x equals 2, or sorry, x equals 3, the limit as x approaches 3 from the left is 2, and the limit as x approaches 3 from the right is 1. So we would say that the limit as x approaches 3 from the left, we put a little minus sign as a superscript to indicate we're approaching from the left. This is because mathematicians love the notation for things. Now we would say that the limit as x approaches 3 from the right is 1. The problem here is that the limit from the left and the limit from the right do not agree. When that happens, we say that the limit doesn't exist. So we'll say since the limit as x approaches 3 from the left of f of x is not equal to the limit as x approaches 3 from the right of f of x. We say the limit as x approaches 3 of f of x does not exist. That's a phrase that we're going to attach to limits. We say that the limit does not exist. Good question. This is just reading this notation. Limit as x approaches 6 of f of x is 2. Intuitively, that means we look at the graph or we plug in some values and we see that the values of the function are headed towards 2. It actually happens at 6 is 100% irrelevant when we're talking about the limits. We only care about what happens near 6. We notice that when we're near 3, we're not approaching anything overall. We're going to different places. Different places. From the left, we're headed towards 2. From the right, we're headed towards 1. Those don't agree. So if I said, what's the limit as x approaches 3? That doesn't exist. From the left, it's 2. From the right, it's 1. Question? That is correct. Does not exist is different than undefined. For reasons. So you wouldn't want to say that the limit is undefined. You want to say that the limit does not exist. Good question. Because those are the kinds of things that we start to mix up when we're new. Any questions? Comment? How's everybody, okay? Terminology day. That's why everybody's looking at me like, oh, hard. Now, we have this intuitive idea of continuity with the pen off the paper business. And we have this intuitive idea of limits. Where's the function headed? We haven't defined what a limit is. We still have to do that because math class. So next week, we're going to talk more about this limit business and how it relates to continuity. We've got a few pieces going already. There's one more thing I have to do before, let me sign off the video. And then I have one more thing to do, and then we'll be on our way. So everybody have a good weekend, and thanks for playing.